Alright, so now you did the power supply and the voltmeter, hopefully. You've looked at those videos. That's at least a quick introduction to like Scopy and like it's the interface and plugging this device in. We're just going to jump right into it for the next part, which is going to be looking at time varying signals. Of course, you could use that DMM before with the histogram, but it's very, very, very limited. Really, I would only use that for things that change very slowly. We're talking about circuits here in class right now that its time constant, or the amount of time it takes for it to discharge, is very easily under milliseconds, so microseconds even. So we need something that can work with signals that change pretty rapidly a lot easier. And to do that, we're going to be using the oscilloscope. And to generate signals that we're going to be working with, we're going to look at the function generator or the signal generator. If you ever hear me say signal gen, function gen, or wave gen, that's all kind of the same thing here. So I've plugged my 80 ALM in. Let me connect it to Scopy, let it figure it out, do a self-calibration. And I've also reset my Scopy configuration, so that way it's probably a little bit closer to what you will see at home. So we're going to start bare bones. So I have my circuit on my side. I've ripped out all my jumper cables just to give you a restart. And I'm going to be actually looking at what we're doing for Lab 4, which is determining the natural response of an RC circuit. So once we're connected, we've done our self-calibration. This circuit that we're dealing with only deals with a square wave. So we need to be able to generate a waveform. To be able to do that, we go to the Signal Generator tab. This is the Signal Generator instrument built into the 80 ALM 2000. What this does is it will generate a waveform. And notice that it's a 2-channel device, so we can set up 2 waveforms if we really want to. It'll generate a waveform on pins W1 and W2. So let me be clear here. Channel 1 is W1, channel 2 is W2. Why that's important is, again, a lot of people are going to think that when this thing generates a signal, oh, this is my voltage source, these 2 wires. No, the WaveGen creates a voltage waveform in reference to the reference ground. So what we are going to make today, we are going to be dealing with just W1, and the negative supply of the voltage source is going to be the reference ground. So we'll talk about that a little bit more. So this is the Wavegen menu. It looks pretty innocent when you first open it. You get this chart that has like time and voltage on its axes. And why it looks so innocent is because it defaults to the constant tab. So you can use this to generate a constant voltage. However, something we're going to talk about more in labs that we're talking about op amps and some other stuff like that is the idea of a loading effect, meaning that this thing can only drive or supply very few milliamps of current. Even some basic resistive circuits that you've studied in class so far need more than tens of milliamps to run. So anything past, a milliamp is going to actually make this thing chug along, and we'll have labs that actually show you that. And again, that's one of kind of the benefits between a USB device versus a actual signal generator, is that a signal generator will be able to provide more oomph to your waveform, more power to it. But I digress. So you can use this to generate a constant waveform if you want, a DC voltage. Fine. To do that, all you do is you sit here and say, okay, well, I want it to be a volt. So you have a couple options here. You can either type in 1,000 millivolts, or you can change your units here. Now you may notice that there's 2 lines on the screen now, orange and purple. Purple is channel 2. We're not going to be dealing with 2 channels of our WaveGen. We only want to generate 1 signal. So what we're going to do is we're going to turn off WaveGen channel 2, and we're only going to deal with 1. And now if you look at our graph here, I'm going to zoom in a little bit. So to zoom in, you have 2 controls here. You can click and drag, and it creates a window over which it'll zoom in. If you right click, it resets the view. So if you look at it, it is generating a 1 volt signal. Now we've said that that's like 1 volt DC source, but it's a 1 volt signal at the end of the day. What if I want to make something that actually changes with time? I don't know, like what our lab's going to be asking for. So now you click the waveform tab, and all of a sudden now it changes into something a little bit more exciting. you have many different options here for your waveforms that this thing can generate. It can generate a sine wave, square waves, triangle waves, trapezoidal waves, literally looks like a trapezoid, rising ramps, falling ramps, all these different things. And if you notice, I'll go back to the sine wave, each one of these have their own sort of sets of parameters that you need to verify with. So for example, for our sine wave here, right, I can change its amplitude from peak to peak. So if you notice, it's going from plus 5 volts at its maximum to minus 5 volts at its minimum. So that's 10 total volts between the peaks of our waveform. If I want to lower that, you can either use the plus and minus buttons. You can scroll over this knob and it acts like a knob on the instrument, which is kind of cool. If you have a very sensitive touchpad like I do though, don't necessarily recommend it. Or I kind of end up doing this a lot, I just type it. The offset, and of course, you know, if you don't have it, like I don't have a circuit set up. Look, I have nothing here set up and hooked up yet. Feel free to mess around with this. What's really nice about this is this thing on the left is your preview window. So if you're really curious about what an offset does, I don't know, what happens if I add a volt offset? Huh, that's interesting. It looks like it takes my sine wave and basically applies a DC offset based on what I set here, and I can move this waveform up and down as I will with this with the knob. I could do this all day. I'm going to reset my offset to 0. Frequency. So how often is this thing going to be changing for something like a sine wave? How many of these, you know, how often or how many of these cycles of peak to peak are there going to be per second? 1 hertz, 1 of them per second. 10 hertz, 10 of them per second. 100 hertz, 100 of them per second. Now here's what you might notice. See, with the amplitude, when I change the amplitude, it's very easy to see what's changing, right? Same thing with the offset. Frequency, it doesn't look like anything is changing. Look at your time base. Look at your x-axis. 0, 2 milliseconds, 8 milliseconds. If I go back to a 1 hertz wave, we go back to 1 second. So that is completely up to you. You have to kind of take a look at that and verify like your time base is correct. So 1 kilohertz, 1000 hertz. So you can generate up to a megahertz and down to millihertz. There are limitations to this thing, so I wouldn't really... Once we get into megahertz, I start to worry about the breadboard, to be honest. It's not going to get damaged. In fact, the breadboard's just going to wreak havoc on your circuit. But for most of the labs, we're going to be dealing with kilohertz range signals. And then lastly, we have phase. What does phase do? I don't know. Let's see this. Whoa, okay. So what phase is doing is it's actually applying a phase shift to my sine wave. So these are all things that we're going to talk about a little bit later here when we get to you know, sine waves and frequency dependence and things like that. For Lab 4A, or Lab 4, I'm sorry, I'm teaching IDS at the same time. For Lab 4, what we need to do is we need to generate a square wave. Our square wave needs to go from 0 volts to 5 volts. So how do we do that? Well, I can use my preview window here to actually build my signal. So I know I need a square wave. Great. So I have my square wave, and here's my prototype. I've changed nothing. This is just the default. If we look at it, this looks right, but there's a problem. Look at the range of values that it takes. It goes from 2.5 volts to minus 2.5 volts. For our lab, we needed to go between 0 and 5. So you can sit here and mess around with these options here, but what you need to do is you go, well, the peak-to-peak voltage is correct. All I need to do is apply an offset. So if I offset it by 2.5 volts, what that means is basically when it goes to the bottom half of the wave, instead of going to minus 2.5, it goes to minus 2.5 plus our offset value, so 0. So this is the way to generate a 0 to 5 volt signal using the Wavegen. You can also change the frequency here. For example, I think for our test circuit with a 1 kilo ohm resistor and a 1 microfarad capacitor, it's a millisecond time constant. So I really want to only deal with maybe like a 10 hertz signal to start with, and then we'll talk about the oscilloscope in a second here. One thing to also note, and I mean, you're not really going to need this for this class, although we might use it at some point, maybe, I don't know. So just a good thing to mention. When you talk about signals like a square wave, you see how they're kind of like discrete values? There's something called the duty cycle. The duty cycle controls how long the signal is on and off for. Mainly used a lot for things like controlling motors and servos, but we can also use this to investigate circuits and circuit behavior as well. And hopefully we'll be able to do that in a couple of our labs. So maybe you've looked down here as well and you've seen noise. What does that mean? Well, I can actually corrupt my signal. So if I wanted, I can add millivolts of noise. I can add volts of noise. And what this is going to do is if I apply uniform noise, it'll actually noise our signal. It'll add noise to it. And you may think, well, that's weird. Why would you ever want to do that? We're going to talk about a class of circuits called filters. The idea of a filter is to help get rid of things like this noise. So we can actually do things like Gaussian noise, Laplacian noise, all sorts of fun stuff here. Things like this. I would consider this to be more digital noise, more jitter noise. So there's a lot of, every time I keep to go look at this thing, it's just, there's so many things that this thing can do. It's crazy. And of course you can do this on normal function gens as well. Last thing I did want to mention here was you can also make a waveform based on a function if you really wanted. There's that's a whole video on its own. But you can also do a buffer. Excuse me. So powerful, it just needed to escape. You have a buffer here. So what you can do is, again, this is another video, but you can build something called an arbitrary waveform. An arbitrary waveform could be something like in MATLAB, maybe you could generate a sine wave or a cardiac sinusoid or all these different signals. Maybe you know what a signal from a piezoelectric element looks like and you want to measure or you want to be able to supply that to your circuit. You can do that. These are really cool. I mean, I really recommend that you all take some time and actually look at it. But back to the lab at hand, we've made our square wave. We can adjust whatever we need to in the panel. Once we're ready, we can hit run. Now, as soon as you hit run, I'm going to hit stop because I haven't hooked it up to a circuit. Sorry about that. Once we hook it, or once we're ready to go, what we do is I need to hook this up to my circuit. So I'm going to take and begin wiring things up because what else are we to do? Again, note that we're using channel 1. Channel 1 comes out of the W1 pin, okay? So what I need to do is take my W1 cable, attach a jumper to it, and take the pin part of the jumper, and I'm going to put it on the input of our circuit. Now for the lab, the input to the circuit is going to be the leg of the resistor. Anybody who wants to, is an astute student of PECA would be able to point out, well, wait a minute. I need a negative part of my supply, right? Clearly a voltage supply is just raising voltage based on a reference point. That's what it does. So, as I mentioned before, the signal generator is referenced to the reference ground inside of the device. So you take one of your black cables from this middle pin here that has the reference ground symbol. So the jet black cable, it's solid. It shouldn't have any patterning on it. I'm going to attach a black jumper. The color doesn't really matter. I'm just using it for uniformity. So we're going to take our reference ground, and I'm going to hook it to the negative leg of our capacitor. Now, to get a 1 microfarad capacitor, I have to use an electrolytic. So that's where if you hear me say the negative leg, electrolytic capacitors have polarity. They have a positive and a negative leg, but more on that in lecture and some recitation stuff. All right. Awesome. So now we've hooked up our Wavegen. Once we're ready to go, we've inspected for shorts, we can hit run. And that's it. Doesn't look all that exciting, but that's because we're not actually visualizing it. I guarantee you things are happening. They are. We need a way to look at it. So what we're going to do is we're going to jump over to the oscilloscope. The oscilloscope is going to be our way in this class to be able to visualize the signals and the properties going on. An oscilloscope can only measure voltage, at least these ones. You can buy things called current probes that allow you to translate current into voltage, and they're really fancy stuff. But at the end of the day, this thing can measure voltage and voltage only. What you have here is as soon as you open the oscilloscope, you're greeted with something that can actually be a little bit complex. when you first look at it, but it's really not that bad. So first off, this viewer in the middle, this graph, you can see that it's set up like a grid, right? Well, it's exactly that. You have control over the x-axis and the y-axis. The x-axis in this graph is time. The y-axis is voltage. When you're using a digital oscilloscope, really what it's doing is it's doing exactly what you would do in the early labs of the voltmeter, where you take a measurement, write it down, take a measurement, write it down, except for instead of you doing that once every like couple of seconds, like the scopes in the lab, for example, can go up to, I don't know, 10 to 20 gigasamples a second. You heard that right. That is 10 to 20 billion voltage readings per second. It's an amazing piece of technology. This, I believe, is in the megasamples per second, which is still very good for what we're doing in this class. It's very good for a USB device. So, and for the price range. So, what this does is it allows us to view these signals. Can you imagine trying to watch something changing 100, 1,000, 10,000, 100,000 times a second? No. This is kind of a time capsule. This is like a time machine. It's really cool. So we need to set up how this thing runs. So how this thing runs is it'll take values all at once, but it needs to know a couple things. It needs to know, well, what scale should I be set at for you to see what's going on? You know, what scale are my voltage readings going to be at? It wants to know also, we're going to talk a little bit about triggering, is it needs to know what to look for in terms of, hey, is this what you actually want to measure? So we're going to do a very basic trigger setup, but there's an entire video that can be made about trigger settings and how to pick them for your circuits. So let's do a basic reading with our circuit here. We want to measure the time constant of this RC circuit. Great. So here's what we do. I open this up, and this is a brand new installation, or not installation, this is a brand new configuration. I have not changed anything. Right off the bat, you should also see that my scaling's a little off, but if you look at it, you actually get a reading on your cursor when you move it around. So right now it's minus 2.2 microseconds and 3.3 something volts maybe. This is very useful to be able to look at specific points in your graph and things like that. And one thing I want you to note as well, notice that the text is orange. That means that it's focused on the channel 1. If I click down here to channel 2, you'll notice something. Look over here. This indicator will change to purple. That's because purple was below this thing the whole time. We'll talk about what that does in a second. But also, my text is turned purple, so it's taking things in reference to channel 2. Let's go back to channel 1. Okay. What are the settings? Why can I just hit go? Yes, no, maybe. It depends. So, I know for a fact what my signal generator is set to. 10 hertz is the frequency at which I'm generating, and I know what measurement I need to make. I know what timing my measurement needs. I know that because I'm generating the voltage. So what I need to do is figure out a time base. This time base here is per division. What that means is that right now it's set to 1 microsecond. Every single one of these steps is 1 microsecond. So there's 16 divisions across the entire scope field here. So if I go all the way to the left, minus 8. If I go all the way to the right, it's 8. So you can change basically the scaling on the x-axis. 1 microsecond, that is insanely fast compared to our generated signal. I want to bring this into the realm of reality. So if I want to actually see, let's say, one of these waveforms on my graph, if I'm so far zoomed in, I'll only see like the flat part. I want to actually see the transition. So what I'm going to do here is I'm going to change my time base to match what my Wavegen is doing. So my Wavegen is at 10 hertz. That is 100 milliseconds per cycle, between each cycle. So what I'm going to do is I'm going to set my time base to be, let's say, 1/10 of that, 10 milliseconds per division. And we can change this. It's not a one and done thing. We're not going to mess with position just yet, and we're not going to mess with a lot of these things down here. What I'm going to do, though, is we also need to look at the vertical division. So vertically, you can also control each step here. So right now it's set for 1 volt per vertical division. I am sending in a 5 volt signal peak to peak. That means I should probably expect to be reading a 0 to 5 volt signal. What that means for me is that there are 10 total divisions vertically, 5 going positive, 5 going negative. So if I really want to get a good look at this thing, I don't want it to like clip up here and get out of the view of the scope. Instead, what I'm going to do is I'm going to set this to be 2 volts per division. Why am I doing that? Because then at least I'll be able to see my entire waveform, and then if there's any sort of anomalies or anything like that, I can catch it. And again, this is for basic measurement. Alright, so we set it to 2 volts per division. Just for the purpose of this video, I'm going to change my channel thickness. It'll change the line drawn here. Now, am I ready to hit go? Sure, you can. Let's see what happens here if I hit run. Well, nothing, because, haha, you need to actually plug in the oscilloscope to be able to measure the oscilloscope. So, how are we going to hook up the scope? This scope is differential, just like the when we talked about the DMM. The scope is a differential reading. What that means is that it's literally taking the voltage reading between the solid orange wire and this orange and white hybrid wire. So the difference between these two wires, the voltage, is what's going to be measured here. So what I'm going to do is I'm going to take a orange wire, plug it into my channel 1 of my oscilloscope. And what I want to do is I'm measuring the voltage across the capacitor. So I'm going to put this, I want to measure positive, my positive reference lead. I'm going to put on the one leg of the capacitor. And now, since it is it's a differential measurement, I need to make sure that I tell it what to measure between. So I'm going to take this orange and white cable, which is 1 minus. What I already plugged in was 1 plus. 1 minus. I'm going to take that, and I'm going to put that across my capacitor here. So I'm measuring the voltage across the capacitor. So once we're good with that, we're ready to turn on our scope. So let's see what happens. I hit run. And we get an exciting looking waveform here. So what's going on? So you can do a couple things here. If you see something weird like this happening, you can do a couple things. You can just hit stop, right? So you can just hit stop and it'll just stop data acquisition. You can hit single. And what happens there is, we'll talk about that in a little bit. It basically fills the screen once and it says, here's your readings, and that's it. So I want to hit something home too. Down here you'll see something called a curve style. You don't have to do this, but I want to point this out because this is something that I think is very important to realize. This thing has a finite resolution and it has a finite sampling rate. It looks like it's a continuous measurement. It looks like if I were to zoom in infinitely, that it would be a continuous line, infinite number of dots. In reality, if I were to zoom in here, there are only so many dots. I forgot to turn off channel 2. There are only so many dots and measurements that are being made. These are each of the individual discrete voltage measurements that it's making. And you can see the time between them. That's set by the sampling time, or the sampling rate of the scope. If I right click, I can zoom back out again. And basically right click is like an undo on zoom. I just wanted to show you that. I'm going to go back to lines. When you put lines, it basically tries to interpolate a line between those dots. All right. So, crazy things are happening. So, what I want to do is this. First, I'm going to change my time base. I don't want it to be a millisecond. What's happening is that my signal is too slow for my current horizontal time base settings. So, it's happening way longer. It's like zooming in on a wave, right? You're only going to see a little bit of this giant thing. So what I want to do is I'm going to zoom out. So I can do that by entering a number, scrolling on the knob, or I can hit up the plus button, and I'll do that. So basically what I've done is I've said, hey, look, instead of zooming in and taking a sample that quickly, instead I want to take readings over a longer period of time. I want to look at a longer period of time. So again, this thing is just a rolling capture log of voltage measurements. It's sitting there making these measurements, and it's saying, here's my history of them. So I'm going to hit run. that looks a little bit more like a square wave. It has some weirdness, but that's because we're measuring an RC circuit. So you see how it's dancing around here? That's really annoying to try and like measure certain things. So again, you have a couple options. You can hit stop, you can hit single, or we got to do what everyone is afraid of with these scopes, triggering. The idea with the trigger is what it's trying to do for you here is trying to center what it thinks is the center of the waveform you're trying to measure. Right now, that trigger point is probably on 0. And you can see that it's not exactly 0. It's going to have some noise there. So it's constantly moving back and forth and saying, I think you want to look here, no here, no here. So what we got to do is we got to tell it, hey, it's okay. We want you to measure, we want you to look for a falling edge or a rising edge. And I want you to put that at my t is equal to 0 axis. So to get to the trigger settings, you go down to the bottom right, and you hit this little taskbar thing. Right now, it's set on auto mode. I'll talk to you about what that means in a second. We want to say our source is channel 1. We're trying to make a measurement from channel 1. Our triggering should be on channel 1. We're going to use an internal analog signal. And here's what I want to look for. Since we're looking for the natural response, I want to look for a falling edge. So I want to look when this waveform goes down, which is something like right here. I want to see when this waveform scoots down and tries to decay down to 0. Now here you see level. We're not going to worry about the hysteresis just yet, but the level is actually what is our trigger level. Now if you look, I'm moving the knob and you see that thing going up on the right and left. This right here is our trigger level, and this is something you would see on a traditional oscilloscope as well. There's actually a trigger knob normally, like an actual discrete knob, and as you move it, this level goes through. So what our conditions have said right now is I'm going to set this arbitrarily to 3 volts. What has happened is I'm saying, okay, I want you to look for a falling edge, and once this falling edge hits 3 volts, I want you to say that's t is equal to 0. So I want you to try and line that up. So now if I hit run with the trigger, look what happens. Now, just to clarify again what's happening, this thing is constantly reading. You can see these little changes here and there, little jumps up and down. This thing is taking an active reading. You are getting a snapshot of something very quickly happening on your screen that you can visualize. It's really cool. You're watching a signal that, is traveling, some fraction of the speed of light. But what this is allowing you to do is by setting up the trigger method, it's lining up the center of my screen. And if I scroll down here, if I look right at if I try to line this up with t is equal to 0, like right about there, if you look right there, it's about 3 volts. I can't move my cursor that well. But if you want proof that this is live, I'm not going to stop this thing. I'm going to go to my SigGen, and I'm going to up the frequency. And look what happened. It changed live. Go to my SigGen, drop my frequency, and it changed back. So what if I wanted to look more at this portion right here? So again, this is running live. So I can click and drag to make a zoom window. And now it'll zoom in on this part, and this is cool. If I heat up this resistor, if this was like a thermistor, and I might do this as an exercise, and I touched it, you would actually watch the time constant change as I would touch it, because the thermistor would change its resistance. But, cool. We're in the part of the lab now where, hey, I have my natural response of my circuit. Well, it would be really nice if I could take a measurement, right? So, how do I do that? We have these things called cursors. I can enable the cursors with this little checkbox. And I'm going to go to the cursor menu. So to get to the active menu, you hit this little setting thing. One of the first things I want you to realize is that you can move this menu around. See how it's like blocking our signal up here, this like cursor menu? I'm going to move it to the right. So, really awesome. That was so cool to find. So here's what I want to do. Is I need to find when I need to find the time constant. I want to measure the time constant of the natural response. So the time constant is going to be when the capacitor voltage discharges by a factor of E of what it was originally at. So we've held it at 5 volts for a long time at this part here, and then we said, okay, start discharging. So I've done the math ahead of time, and I know that dropping by a factor of E is about dropping by 63%. So that's about when the voltage here hits 1.85 volts, the amount of time it takes for it to do that, that's our time constant. So here's what I can do with these cursors. Let me turn off the cursors and turn them back on. When I turn them on, you get these gray lines that pop up. They're cursors. 2 of them are for the vertical or for the horizontal axis. These are the ones that are vertical. I know that's a little weird to hear. But if you look as I'm moving this around, keep an eye out for cursor T2 as I move this trigger or this cursor around. So it's taking a measurement. It's telling me where in time is my current measurement at, or my cursor at. If I move trace 1 or tracker 1 or cursor 1, I can do the same thing. Now what's really cool about cursors, and I mean this is again something that's very common on most oscilloscopes, is the reason that you use cursors are to take differential measurements. So for example, I need to look at when, I'm trying to match when the time constant happens, right? So here's the deal. You also have these ones that go along the vertical axis. And if you look, they're V1 and V2 as well. So here's how I'm going to approach measuring the time constant. You could sit here with your cursor and like do this. You can do that if you want. Here's how you can use cursors. So I'm going to try and plant this right at 5 volts, or right at the maximum voltage that this thing is going to be at. So right about here. So it's about 4.8 volts. If I do some quick math real quick, I don't even have my calculator on me. I'm going to still look for about 1.85 volts. It should be a little bit less, so maybe 1.8 volts. You can do the math if you want. But again, I'm looking for a drop in 63%. By 63%. So originally that was going to be around 1.85, and it's probably going to be a little bit lower now, but just bear with me. 1.85, and you try to get close enough with this value of cursor 2. And now look, delta V tells you how much it's changed by. So 5 down to 1.85 is about that value. So I have 1.85 and I've got 5 volts, roughly. I've got the maximum voltage. If you really wanted to, you should calculate it, and maybe it'll be a little bit lower. So here's what you can do. We then you don't move this point. This point here, cursor 1, is going to be our starting point. What we've now built is this big intersecting system. So my starting point is, and you're basically building a coordinate system. My starting point is at t is equal to minus 573 microseconds, and the value is 4.811 volts. I've now found the value, or the vertical value, or the voltage that I'm targeting. I can now move this cursor until it intersects with the horizontal cursor number 2 and the wire. Now, if you use cursors and you've done things correctly, what you end up finding is, one of the nice things about cursor measurements is that they tell you things like delta T and delta V. Look at the delta T value. That is almost perfectly 1 millisecond, which is the actual time constant of this RC circuit. So for us, that's an amazing thing. It allows us to measure the time constant. And that's just using cursors. We can do all sorts of things with this thing. We can do measurements, for example. So I'm going to turn off the cursors and turn on measurements. And I can measure all sorts of things. I can measure statistics, frequency, rise times, widths, duty cycles. So, if I wanted to look at the rise time, right? So let me enable the rise time stat. Excuse me. Or fall time. What I can do is I can see roughly how long it takes for this circuit to fall, the time it takes to fall, and there's all sorts of fun stuff that you can do with this. I mean, Again, this is more videos that need to be made to talk about all the features on this. But there's so many different measurements you can make. It is crazy. Area curves. You know, you want to actually calculate things like power and charge. You can do areas. You can pick cycles for areas, middle grounds, amplitudes, highest values, lowest values, overshoot, undershoot. It's so many cool things, and it's up to you to really try them out. So, at the end of the day, this is how you can get to the time constant measurement. And if you wanted to save this for later, if you make this exact circuit with the 1 microfarad capacitor from your kit, a 1 kilo ohm resistor from your kit, and I'm going to save this profile as lab 4 time constant measurement. You'll be able to upload this and do this on your own. What I recommend doing is reviewing this and kind of messing around with some of the settings here. So I'm going to get out of the measurement tool. I'm going to go to cursors, and actually I want to save it with the cursors on. Oops. What did I call it? Lab 4 constant measurement save, and I would like to overwrite it. Thank you. So what I want to do is, for the other parts of the lab, you're basically replacing C and replacing R and measuring new time constants. Remember, if you need to measure things, or if you need to, say, look at something that has a longer time constant, you can mess with the time base. I can zoom out. Now, your cursors, you're going to have to move. But you can investigate this curve, and that's the beauty of this tool, is just the sheer amount of information available to you is insane. You can zoom out and see a bunch of cycles of this thing. We can just zoom it to see fine detail. And sometimes when you do quick zooms like that, it actually freaks out a little bit and it has a buffer. But there's some more advanced stuff that I want you to look at later. But for now, try this out. Play around. See what's going on. So in this video, we talked about, in kind of a long form, almost 40 minutes, we talked about the basics of the oscilloscope, and we talked about the basics of the SigGen. The signal generator was able to provide us with a custom waveform that we wanted to look at, and the oscilloscope is actually something that we can use to view electrical signals. And again, I love this thing because it allows you to see things that are moving at tens to hundreds to thousands of times a second, and we're able to actually view it. So hopefully this helps out. Go ahead and try this for Lab 4A. Try things out. If you have questions, let me know. Otherwise, have some fun. Mess around with certain things. And again, have fun.